Let's get started.
Everybody. So real quick, we're just going to introduce ourselves. We're going to start the presentation here. My name is Tyus Green.
I'm Nicholas Chalik.
We're from Team 701. We're going to be going over the pros and cons of Neo motors. So just real quick, that's awkward.
Oh, Alt-Tech.
Oh, right. That's even more awkward. So Nick's going to set this back up. We're just going to be going over the pros and cons of hardware. Then we're going to go over software. Then along the way, we're going to go over our experience on Team 701 using these products. So in case you're in here for the wrong meeting, I doubt it. We waited an extra 10 minutes. If you didn't figure it out by then, oof. So we're gonna be going over these topics right here, okay? Starting off, we just want to get a quick view of the audience. Who here knows the difference between brushless and brushed motors? Okay, so like half of us, cool. I'm just gonna go over it real quick to break it down. In FRC and FIRST, we're used to brushed motors, okay? That includes our Sims, Mini Sims, 775 Pros, various bag motors, all right? Neos are brushless, and what this means is that we're dealing with a whole new setup and how the motor works. On brushed motors, as you can see here, we can feed in power straight through one side. It'll make contact with something called a commutator. That commutator will bridge connection into these electromagnetic coils, and this is the rotor. These coils will turn on, create an electromagnetic field, and then respond with the external stators, which are just permanent magnets. In that way, it'll start to spin, and as it spins, the commutator will churn, the brushes will physically hit a new commutator and change the electromagnetic field created by these coils in the center. So, by just giving this motor power, we can have it run constantly. We have no need to control, which part of the commutator needs power because it spins and changes polarity all the time, so we're fine. On brushless motors, we have a bit of a different setup. There's no commutator. In fact, we're making no connection with the actual rotor, all right? Instead, we have the electromagnetic coils on the outside. We have our rotor be the actual permanent magnets. And in this way, we can increase our efficiency because we're not physically wearing down the rotor by touching it. And it'll spin at about 90% efficiency, whereas brushes will spin with approximately 75 to 85% efficiency. Of course, this comes with a few problems in itself because we have to make sure we time the electromagnetic coils to fire at the right time and also make sure that they fire in the correct polarity. So that's just a difference between the two. First thing we're going to go into is a Neo Pro, high torque and high speed. As I was talking about with the efficiency, these motors are going to spin with a much higher torque and a much higher speed than most of the other motors we're used to. And that means that right off the bat, we're going to be getting a lot of power out of these things. On our team, we tested these Neo motors just on a super lightweight chassis. We put down 4 Neos, just a quick little West Coast drive, wanted to see what we could do. Put out max power, yeah, we could get no traction. It was just Tokyo drift all along the carpet. It was just going crazy. And one thing we learned right off the bat was that we need to make sure we gear these things correctly, okay? It can be used for a variety of things because they're so much more powerful than your regular motors. But you got to make sure you can harness that power correctly and not cause slipping in your chain or start having a drivetrain that you just can't control. So real quick, we're going to give you a demo of the motor running. I'm going to have my friend Nick here pull up the controller. Yeah, come on. There we go. So as we can see on the Neo as well, we have 3 power wires. That's to correspond with the different electromagnetic coils. And I'm plugging in an encoder to make sure that we can detect where the coils are in relation to the magnet, and therefore have the spark understand which coils to fire. Give it power. All right. And then just a quick little test run just to show you guys. Go ahead. Oh. Yeah, so run pretty quick here, pretty high speed. All right, we're good, we can cut it there. First time we turned one on, someone held it in their hand, bad idea. It just turned on, whipped right out, fell on the floor, disconnected itself. So make sure you have these things tied down tight, or when you're testing them, be careful. Now moving on to the next Pro we have here, they're compact and they're fairly lightweight. They are pretty small and they pack a lot of power for how much weight they're using. It's just under 1 pound. And as you can see here, this was the gearbox we were using for our drivetrain this year on our Valkyrie robot. as you can see, this has 2 Neo motors and the gearing needed to run chain across a West Coast drive, as well as we mounted a little 3D mount for our sparks on the top here, and it's pretty light and really, really small as compared to other motors. All right. Of course, that means that you're just going to be having a lot more weight that you can use for other things and a lot more space to be utilized for actual movement of various arms, objects, things like that. All right, so breaking down a quick hardware comparison with other motors that we used before, I highlighted in yellow like the best of the 3. So starting out in just length and size in general, the Neo is the best out of a Sim and a 775 Pro. It's really small. The weight, again, just under a pound, and that's barely beaten by a 775 Pro, which is mainly utilized for free speed and has almost no torque, as you can see. Moving into max power, Neos are going to be pulling a lot of power, the most power of these motors. The reason this is going to matter is obviously because if you have a lot of motors on your robot, you set them all to max power, you're going to expect to be draining your battery a lot faster. Right now, we're prototyping a new robot just to train our rookies up this year. We've decided to use arm motors, elevator motors, drivetrain motors, intake motors, all Neos. In fact, I don't even think we have pneumatics this time. So we're expecting to be drawing a lot more current, and therefore we need to plan our battery cycles to be much more efficient. That's one thing we had to talk about. So it's a quick breakdown. And in terms of pricing, Neos cost $40. The Spark Max controller for it, $75. As compared with other motors, a Sim will cost about $32 and a 775 Pro about $20. So just some pricing ranges there just to show you the benefits about that. All right. One con to the Neo is that we have a lot of wires running here. Usually when we're running those other brushed motors, we just have 2 power wires running over to our Talon or Spark or Jag. I don't know, we use Jags. And it's not much to worry about. With a Spark, we have to have 3 power wires around 12 gauge and 6 encoder wires that are extremely small, 24 gauge. All of that has to be run back to the Spark. And because of this, we've planned for our robot that our Spark will be right next to our Neo. In fact, as we can see right here on this, we put them right on top of the Neos. We didn't want this to have to travel too far because that's going to mean, A, you're taking up more space with your wires and having to route that all. And also it's making more, I don't know, chance for damage to be taken to your wires, right? Small wires over long distance, bit scary, especially for moving giant arms and elevators back and forth. And in terms of how much wire they give you right from taking out of the box, you have about a foot of length to go, all right? One cool thing about the Spark is that the Spark can also be doubled as a brushed controller. So as I just talked about, it's mainly here to try and run these Neos, but you can actually switch over to a brushed mode in your Spark client. And Nick will be going over how we do that in the Spark client later in his presentation. But we can just switch over the wires that we're using the red and black to run a brushed motor, switch the mode in the Spark client, and then we'll be able to run it from there. So this, of course, kind of opens up the idea of like, oh, do we even need, you know, Talons anymore? Or that's just kind of like thrown in the dust. In a way, you could try and do an only Spark robot, and you would have no need for Talons whatsoever because this would double as the brushless and brushed modes. So yeah, and of course that would mean that we're not using the encoder port on the end there. All right, another thing here, as far as I can tell, these are brand new crimps that for these. These are not PWM crimps that are that nice, like all slide in for locking, stuff that you've seen in Vex. The power poles are gonna stay the same. It's still these Anderson power pole crimps, but these new ones are gonna be pretty new to most of us here. You can buy these. They're JST PH contacts and housings. You can just buy those off of DigiKey. They're pretty cheap. And then that means that we're gonna have a new crimping tool. It'll be hard to use your regular PWM crimping tool for these, I've found. And you can just buy an iWis crimping tool on Amazon, and you'll just use the very end of the nose to get those crimps on. So of course that means you're gonna have to just be spending a bit more, and you're gonna have to be keeping track of a lot more crimps when you're putting together and working on repairs. Also, if you want to do extensions for the encoder, like I said, it was a foot length of extending that out. You have to cut it and either restock your wires on, or you're gonna have to put in new crimps to put it all together again. So there's that. Another big con, the encoders. So we all love to be able to, you know, track our robots as they're moving, whether we want an autonomous mode or we're just trying to push the button and then it'll drive 6 feet or move the elevator up so high. We won't be able to track that, right? So the Spark uses Hall effect sensors on the inside of the motor to keep track of where the rotor is. And these Hall effect sensors are just encoders that are used to run the motor and keep track of how it's working so we don't break it, right? And the data coming from that wire is actually tied directly to the data port on the top of the Spark Max. And we're going to talk about why that's important in a minute here. But the data that we get from this, we can access. Okay, we can actually pull that data out when we're programming our robot. We can view it, but we have a small problem. It's only 42 ppr. Okay, ppr is essentially the pulses per rotation, and in a sense, it's the ticks you can get every rotation, right? So if we can check each instance of our rotation in 1/42nd of a rotation, that's not the best. Mag encoders are running at about 1024 ppr, which is giving us a much higher accuracy and be able to get a lot more precise movements when we're running through autonomous. So that's not going to be the best way to keep a robot. We could gear that into torque, and then we could extend that 42 ppr to a lot higher from our output shaft, but we get the problems of backlash. Right here, again, just to explain exactly what's going on with the encoders being tied to the data port, because I'm going to talk about this in a second, as well. So normally, we have our mag encoders, right? We want to hook these up and get a nice high 1024 ppr, really well-defined positioning for our robot. It's great precision, but we're going to have to circumvent the actual data port on the top. When you hook these up, you'll probably put a ribbon cable running from the encoder over to your Talon SRX, and you're good to go. We can interpret the data and give the Talon code for it to understand what to do in response to the data. But the encoder pins on the top of the data port in a Spark Max are tied to the encoders inside the motor. So if you put an external encoder on the top of the data port, it'll have a bunch of data clashing with itself, and it'll A, fry one of your encoders, and B, probably stall out your motor and could end up breaking it. So we have to go around using the Spark Max, which becomes an issue. We have a few fixes that we've found to help get data from the external encoder and still run it back to the motor controller. We can hook up the encoder to a breakout board, and then from the breakout board, run it to a canifier, and from the canifier, we can put it on a CAN network, and so that it can be interpreted and send the information over to Spark Max. Canifiers are essentially a Talon, but no motor control. It's just this nice long PCB that'll give you all of the computing power that a Talon has, but it's not big, it's not bulky, and it's not redundant. It's doing just the information of collecting and interpreting data from your encoder. If you don't have a canifier, we can always just use a straight breakout board. You can run the encoder to a breakout, and then from there, you can solder some wires to send the breakout straight to the DIO pins of your Robo Rio. And then from there, you'll be able to interpret the data on the Rio and then send the data via CAN over to the Spark Max. This one is going to have a bit more redundancy since we're having to move the data to the Rio to get interpreted and not straight on the board that's on the next to our Spark, but it still works. And then I'll show you a quick representation of this. If we have our ribbon cable set up to an encoder, we'll have to set up 5 volts for the breakout board and then also ground, and then hook up ports A and B on the encoder. If you go on the website and look at the pinout, you'll be able to see that a bit more clearly. Hook that up, and then we'll go to the DIO, and then where it says S, we'll plug in the signal for the first one. Put your 5 volts in your ground where it says 5 volts in ground, and then take your second data pin and just go to the second DIO port and connect that up to the signal port there. So we'll be using 2 DIO ports with the breakout board. If we have none of this, we could always use a dummy Talon, and that's like the least efficient way to do it. It's our last resort. We'd have to put a Talon on, give it power, and then there can interpret the data from the encoder and then send that through the CAN network back to the Spark. But of course, that's big, that's bulky, and it doesn't make much sense. We're not running any motor with it. You have to plug the ports at the end just to make sure you don't get any bridges between the motor output voltages. So not the best idea. It's best to use the canifier or breakout. Okay, cool. And then real quick, do we have any quick questions on the hardware component? If it's something big and long and you want to see some demonstrations, we could do that after the presentation. Anything quick right now? Yes.
So the 42 counts per revolution.
Yes.
It's using 3 Hall sensors inside the motor.
Yes.
So does it do 6-step commutation on the motors?
Oh.
You know?
Actually, the Neo has 14 poles in it, and so not 3. It has 14, and it the PPR is determined by 6.
6 times 7.
Right,
Yeah.
6 times the amount of pole pairs. Yeah.
As far as the 6-stage commutation that you're talking about, I'm unsure about.
Yeah, well, now that it's
Oh.
14 poles, that makes sense.
Oh,
Yeah.
cool. Okay, sweet. Anything else real quick that we can cover? Awesome.
All right. So now that we're done with the hardware part, I'm going to go more into the software, how you would control a Neo using a SparkMax, and what this low resolution count in your encoder means in its accuracy and precision. And we're going to get started off with the firmware. So the SparkMax has a firmware version on it that Rev Robotics will come out with updates every so often, and you download it and upload it onto the SparkMax. With that, sometimes there will be new updated libraries that correspond with that you need to put in your code. So when they come out with a new firmware version, always check to see if there's a corresponding library. There isn't always, but sometimes there is. And you need to get both, or else they won't work with each other. This version number is kept track in your code. In the revrobotics.json file in your code is where all the version numbers are kept track of, and you need to update it manually by typing in the physical change when you do this, because it doesn't update automatically. So this is what ours looked like last year. There are 5 places in the revrobotics.json file where the firmware version number needs to be updated. Do this every time, because it won't do it automatically. So a con about the SparkMax in the firmware aspect is that every time you upload new firmware version, so you update the SparkMax, it resets all of the settings that you had set for it. So like brushless mode, brake mode, coast mode, all that stuff gets reset back to the factory default every time you update the firmware. So in order to get around this, it's smart to set up all your settings in your code as I'm showing right there. Every single setting in the client that you can just set in your code. And that way you don't ever need to update your settings again from the client, because when you run the code on your robot, it will automatically set those settings for you, and you won't have to do it manually. So just another pro for the SparkMax is it becomes very easy to test your motors without much of a hassle. So usually with other motors like the 775 Pros and whatnot, you have to either plug it into, hook it up to a whole proto board and hook up a juice box maybe. Sometimes if you don't have a juice box, you would actually write code for it to run and then run it with your code. But with the Spark, you can simply plug in a battery, power to the SparkMax, and then SparkMax to the motor. And if you have the client, you're all set. So I'm gonna show you guys that real quick, what that looks like.
So on the proto board here, we're gonna give it power real quick. Cool. And then I'm gonna disconnect the Spark we're using from the CAN bus to show you that we're really only operating with a battery, a main breaker, a PDP, and the SparkMax. We're not using any RoboRio, no radio, no code. And then we have a USB-C cable connected in.
Yep.
And I'm gonna plug in power real quick. Oh, there it is.
This is what the client looks like. You'll start out, this is what it'll show up when you first open it. You just make sure that you're running a brushless motor. You have all your settings here, which can all be set in your code if you want to. And then here, there's the run tab. You have a little graph here with PID controls if you want. And then you can click run and drag this to either side that you want. Oh, I didn't connect, whoops.
That'll help. So yeah, for prototyping, a lot easier. Now we don't have to worry about setting up this big grand board, writing some code, or having to worry about, let's see, how many juice boxes do we need to run this, little catapult device? No, we're just hooking up the motor controller to power and then using this client to just run it straight from the computer.
Did you plug it in right?
Encoder, power, yeah, we're good.
Did you plug the motor in while everything was still on?
Might have, yeah.
Oh,
You
yeah,
might just want to reopen.
Yeah, yeah. Well,
So
no, I'm saying like this, if this is still on, and you plug the motor in while this was on.
Oh.
Yeah.
Power cycling.
Okay.
Yeah, with this, yeah.
Yeah.
With the robot too, you're gonna want to make sure that if you're ever doing updates to your Spark Max or to the Neo, make sure you power cycle the robot, or else this will happen, and you'll be like, "Oh my gosh, the new code, it's not working." You're like, "Oh man, the new update didn't go through. What happened?" No, just power cycle. Nothing still.
Well, I don't know what was different from 5 minutes ago, but.
You want to talk about how that's a con? How it's sometimes really
Yeah,
finicky?
well, completely, not reliable at all. But I mean, this usually is reliable. I'm not 100% sure why this isn't working right now, but it really is as simple as clicking that button and the motor runs. You can hook that up to motors that are already on your robot, and instead of, if you want to test one motor, if something's not working, you want to test one motor without having to run all the rest of the motors, instead of having to unplug, all the other motors except for one and then running your code to see, like, is it turning? You can just plug this USB into it and run it, and it will only run that motor, and you don't need to worry about anything else. So it's really good for prototyping and whatnot.
That came in handy so much when we were testing the elevator with our 2 motors, and we're like, oh man, are they going the right direction? We have to unplug a motor, run the code, see if it's working. Oh, yep, it's going the right way. Unplug the other one, plug the other one back in. It's a big hassle.
Right.
With this,
This is one cord.
Huh?
One cord, one cable, you plug it in and click a button.
With this, one cable, click a button, see if it's going the right way. Really easy.
Right. So PID control. As you saw in the client menu, there is PID options for you to set their constants for your PID control. But there comes a problem with PID control when you have the low resolution count that the Neo has. There's 42 counts per revolution in a Neo. And as we discussed before, there are some workarounds around getting higher resolution, but all of those solutions included using CAN as a way to get that information to the Neo. And with CAN, that information only circulates once every 20 milliseconds, I believe.
50 milliseconds.
50 milliseconds. And that ends up not being much better than the 42 counts that are already there. So in order to explain why really that this low resolution count would have such a big impact on PID, I'm just going to go over briefly what PID is, just to show you that this low resolution count has a big effect on it. But real quick, actually, who here knows what PID is already?
Nice.
So one person. Cool. So I'm glad I put this in then.
I'm still.
All right. All right. So let's say we want to run a motor to a certain position, 15 meters. If we were to tell the motor to do that by itself, it would just go speed up as fast as it can and then stop once it hit that encoder count. If you have brake mode on, then it will probably stop, or it might overshoot a little bit, but it'll stop pretty close to where you want it. And if you have coast mode on, it will stop and then keep rolling and you won't land where you want. So PID is used to approach your destination as fast as you can, but also slowing down and ending the whole sequence right at where you want to be in the end. PID stands for proportional integral derivative. Those are terms you might have heard in your calculus or physics class. Proportional just means that, as shown by this graph here, As you approach your destination, you slow down. So this red line is the error line. Error is how far away you are from where you want to be. So if you're starting at 0 and you need to go to 15 meters, then your error line is at 15. And as you can see, as you get closer, the error line gets smaller and smaller. So this is what the graph would look like with motor control just proportional. So the problem with this, though, is that you will never actually reach your destination because you will always get slower and slower and slower as you get to your destination, and you will never actually reach there. So to fix that, we use integral. Integral, by the definition of the word, is the area under the line. So what integral does is it takes the area under the error line and it adds it on to the motor input. And so that's what makes it overshoot, as you can see in the graph. It'll add on to the motor input to make it go further and try to reach that destination. Once you overshoot, the integral becomes negative here, as you can see, because now it's below your set below 0. So what that means is that it'll curve back around, and eventually you won't ever stop oscillating, but you will oscillate smaller and smaller and smaller and smaller every time.
If you ever see an arm using just PI loops, essentially what will happen is it'll try to reach the point and it'll just start wiggling back and forth like a metronome, but
less and less,
slower and slower. And then after a while, just like you'll hear a buzz of it still kind of vibrating. So still not the best yet.
Right. Right, and that will take a while or some amount of time. With derivative, which is the slope of your line, it ends up looking something like this. It takes the derivative of your error line, which is negative when it's above 0 and positive once it comes back around. We'll add that number onto your motor input and subtract away from that overshoot. Derivative is trying to prevent that overshoot from happening, so you can hopefully approach your destination as quickly as possible, slow down as you get there. It's okay if you overshoot a little bit because you can come right back and hit that destination point as efficiently as you can. So now that I gave you a short little workshop on PID, why does the low revolution count actually make it like so hard? Well, it's because it ends up looking like that. It ends up looking like a PI loop. Because what happens is, I'm going to come over onto this side. What happens is we ask, all right, we want to go 15. And the motor's like, all right, let's go 15. So it starts speeding up and it says, all right, we're 15 away. We need to speed up really fast. So it starts speeding up really fast. And then let's say, we get another update of where we are after 50 milliseconds over CAN, or after our motor reaches that next 42 count. We might already be like right here, or for instance, we could be here. Now it says, oh, we're here. We better, we're getting closer. Let's slow down a little bit. So then we slow down, right? And now we're here. And it's like, oh, we're so close. Okay, let's just go a little bit further and not overshoot. But the problem is once you're here, it'll say we're this far away the entire time until you get that updated position. So it will say, all right, we're this far away, we're this far away. Oh, we got an update and now we're up here now. So it makes that overshoot worse with that low resolution count. So basically PID just becomes very inefficient and hard to use. And yeah, you can get around it somewhat with gearing your motor for torque, so that your motor spins more times and then your arm will move slower, or your elevator or whatever. But it's still, even if you gear it twice as much, so you have, or 4 times as much, so you have larger amount of counts per revolution, it's still like not as good as the mag encoder would be with 1024. So it becomes very, very hard to use. And thus far, we haven't found a way to use external encoders with Neo brushless motors without going through CAN.
If you guys figure out a way, let us
Right.
know.
So this is the best thing that we could come up with is, yeah, okay, it works with 42 counts per revolution. It's not as efficient as it could be. And it's up to you to decide whether it's worth using it than not using it at all, depending on what you want. You know, if you need something with absolute precision, then maybe it's not a good idea with a Neo brushless motor.
You might want to just turn to using a brushed motor, then hooking up a Talon SRX, which will have direct data input from the Mac encoder. So whenever you're planning these stages in your robot, make sure you understand that if you want a nice, well-controlled PID loop, Neos are not the best approach to do that. You might want to come back and go to a brushed DC motor.
Yep. Right. Is that worth it to you?
Right. If you want any more extra information, I'd highly suggest going on Chief Delphi. This became a huge topic last year because they were just coming out, updates are happening all the time, and people had this big conversation going on. So always go on Chief Delphi, search up Neo Motor, Spark Max controller, see what comes up. A lot of people with smaller problems that are less frequent are going to have answers to your questions. After that, I highly suggest you read the Neo documentation and the Spark Max documentation that is on the RevRobotics website. Get the nice fine details into how this is working. Once we give it a once over and a nice read through, we became a lot more able to understand exactly how they worked and plan more efficiently for our robot design. So now we're going to open this up for any Q&A. Anybody have any questions?
Real quick though, shout out to our boys.
Citrus Circuits. If you want to give us any feedback, we got a QR code up here, and give any feedback, asking questions.
Right, but yeah, questions.
SparkMax and Neo made by the same company?
Yes, RevRobotics.
Okay.
Yeah.
So they just didn't think about the resolution.
So we're hoping they're going to either come up with the SparkMax 2.0, which will feature an external data port that we can use for the computation of data coming from the encoder, or, and I don't know why they do this, a Neo 2.0 where like the Hall effect sensors have like 1024 PPR, which I don't imagine they do because that's redundant at that point, but they kind of have this all controlled. There's not another company. Yeah.
They could have used one of the magnetic absolute position encoders and then have the controller read that and it wouldn't be all this.
Oh, yeah.
But it's inside their controller that would need to change it to work with it.
Yeah, they could make that update too, and that would work. We should just start sending them some like letters or something. Tell them.
One thing that's actually been on the Rev Trello board is there's a possibility, they're working on, well, it's been on there for months now, but there may be a possibility to sacrifice limit switch inputs, but be able to plug an encoder into that data port. So you sacrifice limit switches, but you get a second encoder.
That's okay, we have soft limits.
So he was talking about, just for the mic, the new update of sacrificing limit switches for that data input that we were talking about. That'd be awesome because what we ended up doing is we just tied all of our limit switches to either a mag encoder or to a breakout board that wasn't being utilized by Spark. And that was able to run the data we needed through the CAN network. And because it wasn't reliant on those like ticks per rotation, it's just like, is it on or is it off? It doesn't matter if it goes through the CAN network. So that would be awesome if they can make that switch.
Yeah, that's like the one thing. It's like, I really wish we could just use external encoders with brushless motors using the Spark.
Yeah, that's the biggest issue with it right now. That's the biggest con.
Probably the biggest con.
Yes?
Question from the live stream.
This is a live stream.
Can you use the Spark Max breakout board with external encoders on brushless mode?
We tried, and we ended up just like skidding our motor out, and we were like, wow, why is that happening? And then we figured it out. So yeah, if you have brushless mode on and you have the encoder hooked up, you'll end up just getting your motor stuttering, and you might end up breaking it. If you put it in brushed mode, you can actually use external encoders just fine.
What's going on when you plug in the external encoder in brushless mode is the Spark is using the Hall effect encoder that's in the Neo to know when to switch the polarity of those poles. So when you override that by plugging in your external encoder, it doesn't know when to switch the poles and ends up oscillating between two positions.
It'll get stuck on two electromagnetic coils being charged, and then they'll just stay in their position, and that'll end up not being very fun for the Neo, and one of your encoders isn't going to have a good time. And as I was reading on one of the Chief Delphi posts, one of the encoders will get fried, which, I mean, we don't like that, right? These are expensive tools. So yeah, don't hook up external encoders when in brushless mode. It's not going to be fun. Anything else? For show.
All right.
Let's see, 7:45. Real quick, if anyone has any questions about, I don't know, wiring or anything, you can come over and check out the board right here and just look at how the wires are made. If you want, you can come up and we'll just turn this laptop around and show you some of the client details. If you want to click through that, we can start allowing you to just check it out and figure out how that works. But yeah, that's all I had planned.
Yep.
Thank you guys very much for coming out.